We were discussing the adjoint of a map, and in case V is a Hilbert space, then if A is from D of A contained in V going to V, then we can define A star also from D of A star contained in V going into V by identifying V with its own dual. And if you have that A equals A star, that means dA equals dA star and A equals A star, of course, and A is symmetric, as I said. Then you say A is self-adjoint. Okay, so now we will see a couple of examples for the adjoint. Okay, so first example. So we go back to the examples which we looked at last time. So V equals W equals L2 of omega 0 1 in fact, and we had D of A equals H1 0 of omega. So omega equals 0 1, and you had that A of U is nothing but U dash if U is in dA. Okay, so so there was one erratum in the previous lecture. So we have that A is closed. So then I said if UN goes to U in L2 of omega and UN dash goes to V in L2 of omega, then this implies, we have seen this before, U belongs to H1 0 of omega. Yesterday, last time I mistakenly wrote it as L2 of omega, so please correct it, and you have U dash equal to V. So this is how we proved that A is closed. Okay, so we now go back to this example. So it is A is densely defined, and therefore the adjoint can be defined. So what is D of A star? D of A star is, according to the definition, set of all V in L2 of omega such that integral V U dash V of AU, so 0 to 1 mod is less than or equal to C times mod U 0 omega for every U in H1 0 of omega. Okay. So this implies, so if V belongs to dA star, this implies that integral V phi dash 0 to 1 is less than or equal to C times mod phi 0 omega for every phi in d omega, because H1 0 omega is the closure of d of omega. And then we have seen, compare earlier exercise on Sobolev spaces, that this implies that V belongs to H1 of omega. Okay, so this belongs to H1 of omega. Conversely, if V belongs to H1 of omega, then you have integral 0 to 1 V U dash dx is equal to minus integral V dash U 0 to omega dx, and there are no boundary terms because for every U in H1 0 of omega equal dA. And therefore you have mod V U dash is definitely less than C times mod U 0 omega, and therefore this implies that V belongs to D of A star. So we have shown that D of A star is in fact equal to H1 of omega, and from this condition here, this implies that A star of V equals minus V dash. Okay, so this is the this example. So now let us go to the other example which we looked at last time. So example 2. Okay, so now again V equals W equals L2 of omega, and then you have D of A is H2 of omega intersection H1 0 of omega. So omega contained in Rn, bounded open set of class C0. Okay, so H2 of omega intersection of omega, and then A of U we said is Laplacian of u. And again this is a densely defined and closed operator, and therefore we now want to compute its adjoint. Okay. So let uv in dfa, then you have integral on omega u delta v, which is equal to minus integral grad u grad v, which is equal to integral omega v delta u. Okay. So automatically this means that if v is in dfa, then v delta u is less than or equal to c times mod u 0 omega. So v delta u is less than c times mod u 0 omega from this relationship, and therefore this implies that v belongs to dfa star. So this implies that dA is contained in dfa star, and also by this relation, this symmetric relationship implies that A is also symmetric. Call this star. Star implies A is symmetric. Therefore you have that, so we claim A is self-adjoint. Therefore to show dA star is contained in dfa. So that is what we have to show. Okay, so let f belong to L2 of omega and u is in H10 of omega. Unique solution minus Laplacian u plus u equals f in omega and u equal to 0 on gamma, which is d omega. Okay, so you denote as usual as g of f. Then we know that g is continuous. L2 of omega into H10 of omega back into L2 of omega. Okay, so it is continuous, and of course g is also self-adjoint. We have seen this in the connection of the eigenvalue problem and so on. So we know that it is symmetric, and therefore it is g is symmetric implies self-adjoint. Okay. Now for every f in L2 of omega, dagger has a unique solution. Therefore, it implies that range of I minus A is minus Laplacian u. So, I minus A is what is minus Laplacian u plus u is in fact the whole of L2 of omega. And G is in fact I minus A inverse, which is a continuous linear operator. So I minus A is an unbounded operator, but it has a bounded inverse. Okay, that can always happen. Okay, so now let U belong to D of A star, and you set F equals U minus A star. Let W in V arbitrary and V equals G of W. So G of W means, so we have that I minus A of V equals W. Okay, V is the solution for that equation, and therefore I minus AB will be equal to W. Okay, so now this is the inner product in L2. So f of V equals U minus A star U V. If you, this is the adjoint, so by the adjoint relationship, this is U I minus A times V, that is UW. Now G is self-adjoint, therefore GFW equals F GW, but GW is equal to V equals FV, which is equal to UW. Fv is nothing but uw. So for every w in h10 of omega, you have gfw equals uw, and h10 omega is dense in L2. So you have gf equal to u, and that means, but g, where does g go? G goes, but range of g is contained in h10 of omega, and by the regularity theorem it is also in h2 of omega, because if you take the solution here, there is a unique solution, okay, and by regularity u is in h2 of omega in fact. Okay, that is a regularity theorem, that is why we have this class Z C0, and therefore you have that range of G which is in D of A. Okay, so this implies that U is in D of A, that is D of A star is contained in D of A, and that completes the proof. Therefore, this implies that A is self-adjoint. So, remark, A from D of A contained in V to V Hilbert is said to be monotone if AUU is greater or equal to 0 for every U in V. Okay, and then it is said to be maximal monotone if range of I plus A equals B. Okay, so in above example, minus A is maximal monotone. Because Laplace minus A is minus Laplacian, and then you know minus Laplacian u is integral grad u square and therefore non-negative, and range of I minus A was the whole of L2. Okay, so that is minus A is maximal monotone. So in fact, you could sometimes say maximal dissipative. So if you have less than or equal to 0, then you say dissipative, and I minus A less equal to V or I plus A equal to V, then you say the I minus A equal to V, then you say maximal dissipative. Okay. Okay. So the above proof can be modified to show A maximal monotone and symmetric implies A is self-adjoint. Okay. Then remark. So if you had a real Hilbert space, we just identified V with V star and defined the adjoint of a map from V to V. Okay, but if V is complex Hilbert space, we can still do this complex Hilbert space. So A from dA contained in V going into V, again you define D of A star is set of all V such that VAU in absolute value is less than C times norm U for all U in D of A, and you have A star B. So A star is now defined from D of A star contained in V. So this is V in V going into V, and A star V U will be equal to V A U for all V in D of A star and U in D of A. Okay, so you can still give a definition. So it does not matter that we need to identify the dual, even if it is a complex Hilbert space, this is equal to 2. Then finally, V and W Banach okay, and A, dA contained in V into W is a closed operator. Then we define the norm graph U on the domain of A as equal to norm UV plus norm of AU in W. Okay, so this is for U in DF. Then A closed implies that U is complete, dA is complete for this norm. So, you take any Cauchy sequence un minus um in dA. So, this is less than epsilon for all nm greater or equal to n. Therefore, then un Cauchy in V and AUN is Cauchy in W, and therefore UN will go to U and AUN will go to some V in V and W respectively, and this will imply that U belongs to D of A and AU equal to V, and therefore the Cauchy sequence UN AUN will converge to U in norm dA. Okay. So, whenever, so dA becomes a Banach space with the graph norm, and this is called the graph norm. So, whenever we want to consider dA as an independent Banach space for a closed operator, we will assume that it is given with this norm. And if V is Hilbert, and V equals W, then you know that dA is also Hilbert with the inner product UV dA equals UV in V plus AU AV in V again for UV in dA. So, this becomes the inner product which will give the above norm, the graph norm, and that completes the. Okay, so this is a rapid revision of unbounded operators.